You've been told your whole life that light is a wave. But if that's true, why can a faint ultraviolet light knock electrons out of metal, while an intense red light, no matter how bright, can't? That doesn't just sound strange. It completely breaks the rules of classical physics, and solving that mystery is what made Einstein famous. Think about something simple. You're standing outside on a sunny day. Light is hitting your skin, your eyes, everything around you. We usually imagine light as a smooth wave, like ripples on water. If you make the wave stronger, brighter, it should carry more energy. That feels intuitive. Bigger waves, more push. Now imagine shining light onto a metal surface. What should happen? If light is a wave, then increasing brightness should increase the energy delivered. So, eventually, that energy should be enough to knock electrons out of the metal, even if the light is low frequency, like red light. Just make it bright enough, and it should work, right? That's what physicists expected. But when they actually did the experiment, something didn't add up. They shined red light on metal. Very bright red light. Nothing happened. No electrons came out. Then they switched to ultraviolet light. Even a very dim ultraviolet light. Electrons were ejected immediately, not gradually, not after building up energy. Immediately. So now we have a puzzle. Brightness doesn't control the effect. Color does. That's strange, because color is just frequency, the pitch of light. So somehow, the pitch matters more than the loudness. That's like saying a high-pitched whisper can knock something over, but a loud, deep drum cannot. It doesn't fit our intuition at all. Physicists tried to explain this using wave theory, but it kept failing, because in a wave picture, energy is spread out continuously, like pouring water into a bucket. If you pour slowly, it just takes more time to fill. So even low-energy light should eventually eject electrons. But that's not what happens. There's no waiting, no measurable delay. Either the electrons come out immediately, or not at all. So something fundamental was missing. Then, in 1905, Einstein proposed something radical. He said, what if light doesn't behave like a continuous wave when it interacts with matter? What if light comes in tiny packets, discrete chunks of energy, like little bullets? Each packet carries a specific amount of energy, and that energy depends only on the frequency of the light, not its brightness. Higher frequency, more energetic packets. Lower frequency, less energetic ones. These packets are what we now call photons. Now rethink the experiment. A metal holds its electrons with a certain binding energy, like marbles sitting in small wells. To knock one out, you need enough energy in a single interaction, not spread out, not accumulated over time, all at once. If a photon hits an electron, it either has enough energy or it doesn't. Ultraviolet photons, high energy. They can eject electrons immediately. Red photons, lower energy. Even if you send millions of them, each one is still too weak. So nothing happens. Brightness just means more photons, not more energetic photons. That's the key. And suddenly, everything makes sense. But here's where it gets interesting. This idea wasn't immediately accepted. In fact, many physicists resisted it because it challenged a deeply held belief that light is purely a wave. Even Einstein knew this was a bold claim, but the evidence kept building. And eventually, this explanation became undeniable. It didn't just solve a small puzzle, it changed our understanding of light itself. And for this, Einstein was awarded the Nobel Prize, not for relativity, but for explaining the photoelectric effect. Now pause And think about what this really means. Light, something we see every day, isn't just a smooth wave. It can also behave as individual, countable events, tiny packets of energy. That means, in principle, you can detect a single photon, just one. Not a beam, not a wave, one tiny quantum of light. For a long time, that sounded almost impossible. But today, it's real. Imagine a camera. A normal camera collects many photons to form an image. More light, clearer picture. Less light, noisier image. But now imagine a detector, so sensitive. It can register a single photon. One tiny packet hitting a sensor. And not just detect it, but record when it arrived, and sometimes where. These are single photon detectors and cameras. They don't just take pictures. They measure individual quantum events, like counting raindrops, one by one, during a storm. And recently, these technologies have reached remarkable speeds. Some systems can operate at extremely high frame rates, approaching billions of measurements per second under specialized conditions. They don't literally watch a photon moving like a tiny ball, but they can reconstruct how light propagates by capturing many ultra-fast snapshots. Think about that. Einstein once proposed photons as a theoretical idea to explain a confusing experiment. Now, we build instruments that can detect those photons individually, time them, use them in medical imaging, in quantum communication, in ultra-sensitive sensing technologies. What began as a strange hypothesis is now practical engineering. But here's the deeper insight. The photoelectric effect isn't just about electrons and metals. It's a window into how nature works. Energy isn't always continuous. Sometimes it comes in indivisible units, and interactions don't always happen gradually. Sometimes they're all-or-nothing events. This challenges our intuition, because in our everyday world, things feel smooth, continuous. But at a deeper level, nature is discrete, built from tiny, quantized exchanges. So here's a thought experiment. Imagine turning down the brightness of a light, slowly, until only a few photons remain, then just one. What does light even mean at that point? Is it still a wave, or is it a single event happening at a specific place and time? That question is at the heart of quantum physics. The mystery that made Einstein famous was never really about metal or electrons. It was about light itself. And what it revealed is that reality doesn't behave the way we expect. Not always smooth, not always continuous. Sometimes it comes in tiny, indivisible pieces. And today, we don't just understand those pieces. We can detect them, one photon at a time.